So what we're going to be doing for the next section is talk about how we can integrate higher powers of our trig functions. So on page 9 of our notes, we're going to talk about integrating higher powers of sine and cosine. Remember your Pythagorean identities. We will be using those quite a bit in this section, and specifically focusing on sine squared plus cosine squared equals 1. And again, remember the variation, cosine squared is equal to 1 minus sine squared of x, and sine squared is equal to 1 minus cosine squared of x. So when you're looking at an integral that involves a power of sine or cosine that's not to the first power, you have to pay attention to whether or not this power is even or odd. And since this power is odd, and again, I kind of use this phrase, if it's an odd power, pull one factor out. So what I mean by that is what we're going to do is we're going to rewrite the integral so that you have a sine raised to the second power and you want a linear sine function. So I can rewrite this as a sine squared x times sine of x dx. And if you kind of look ahead, this part right here, this factor that you pulled out, because we know that sine squared times sine is equal to sine to the third. When you do a u sub, because that's what eventually you'll be doing with all of these, this is what you want your du to look like. We want the du to be a sine x dx. Well, I know that in order for this to be my du, I somehow have to rewrite my sine squared in terms of cosine, because I know the derivative of cosine is a sine. So this is where I can replace sine squared with my Pythagorean identity of 1 minus cosine squared. Now I'm ready to do my u sub. So u is equal to cosine of x. My du is going to be that negative sine of x dx. So then I'm going to pull a negative sign out of my integral, and I can rewrite this as my negative 1 minus u squared du. So then when I integrate, remember, be careful of the negative sign. So the integral of 1 is going to be a negative u, and then it's going to be plus u to the third over 3. And again, it's an indefinite integral, so don't forget to add your c. And then, of course, I can replace my u with the cosine of x. So I have negative cosine of x plus cosine to the third of x over 3 plus c. So for part B, notice this power is odd. So again, I still want to break one of these factors out and rewrite this as a cosine to the fourth x times a cosine x dx. Again, think of this part that you made linear. That's eventually what you're going to want your du to be equal to. Well, first of all, you don't have it. In order to use Pythagorean identities, remember, you only can use this if it's a cosine squared. However, you can rewrite cosine to the fourth as a cosine squared x squared times your cosine x dx. Again, if I want this to my du, I know the derivative of sine is cosine. So I have to rewrite this squared parentheses in terms of sine again. I can replace that cosine squared with my Pythagorean identity of 1 minus sine squared. Now I can do my u sub. So u is equal to sine x. My du is equal to cosine x. So I can rewrite my integral now as 1 minus u squared, all squared, times my du. So now I am going to have to FOIL 1 minus u squared. So that's going to give me the integral of 1 minus 2u squared plus u to the fourth du. So now I'm ready to integrate. So I have the integral of u minus 2u to the third over 3 plus u to the fifth over 5 plus c. And I can replace now my u and bring back in the sine. So I have the sine of x minus 2 times the sine cubed of x over 3 plus sine to the fifth x over 5 plus c. So that's how you can handle integrating higher powers of sine and cosine. Now, what happens is when you have even powers, this is where you want to recall your cosine sum and your double angle formulas. Remember, your cosine sum formula is cosine u, cosine v, minus sine u times sine v. And from this formula is derived your cosine double angle formula. So again, going back to your pre-calc again, cosine of 2x is 1 minus 2 sine squared, or remember there's the other variation of 2 cosine squared x minus 1. So when you have these two double angle formulas, what you want to do is you want to solve for sine squared and then eventually solve for cosine squared. So if I solve for sine squared here, sine squared of x is going to be equal to 1 minus cosine of 2x all over 2. Then you have the other double angle formula, the cosine of 2x is equal to 2 cosine squared x minus 1. Again, you want to solve for your cosine squared. So cosine squared x is equal to 1 plus cosine of 2x all over 2. And if you notice, using your double angle formulas, the sine squared and the cosine squared, it's exactly the same formula. But this is a way to remember it. Sine has the subtraction sign. Subtraction and sine both begin with the s. So that's how, if you remember one, you can hopefully remember both. Cosine has the plus, sine has the subtraction, and both begin with the s. Now, the reason why I'm bringing this out again, because you want to eventually get your integral broken down to either where you have a sine and a cosine in it so you can do a u sub, or get it down to the fact that at least you get these trig functions to the first power. So, for example, when you look at sine squared of x, sine squared of x, again, you can do a double angle substitution. Again, what is sine squared equal to? Sine squared is equal to 1 minus cosine of 2x all over 2 dx. So I can pull out my 1/2 out of my integral, so I have 1/2 times your integral of 1 minus the cosine of 2x dx. Now you need to be really careful of this coefficient in front of your integral. You want to use your properties of integration, and you want to split this integral up into two separate integrals. So this will be 1/2 times dx minus 1/2 times your integral of cosine of 2x dx. Because especially you're going to end up doing a u sub, which is going to change the coefficient in front of this integral, but not this one. So I can then finish this to be 1/2. I can integrate dx just to be my x. Minus, I'm going to do a u sub here. So u is equal to 2x. My du is going to be 2 dx. So I have to divide out a 1/2, which is going to now change this to a 1/4, times the cosine of u du. So here's my 1/2 x. The integral of cosine is just going to be a sine, so it's going to be minus 1/4 times the sine, and I'll just bring back in that 2x plus c. We're going to go ahead and do example B in class together. So moving on to page 10 in your notes, again, here's now looking at integrals with higher powers that have both the sine and cosine in them. Here are some tips and rules to kind of remember when you're doing these. Again, you've got to look at your powers and depend upon, again, they use saying split off a factor. I say pull one out. So for example, here's an example of your integral where you've got the cosine to the 5th, a sine to the 4th. Again, looking at your cosine is raised to the odd power. So whatever your higher power is, again, you're dealing with the odd ones. Pull one out. So you're going to make one of your factors linear. So I can rewrite this integral as a sine to the 4th x, cosine to the 4th x, times your cosine of x dx. Again, this is what, if you're looking ahead, what I want my u to be equal to. Again, I know that the derivative of this is going to be the derivative of sine is a cosine. So what I want to do is I want to rewrite my integral in terms of all sine if I can. So when I take a look at example that cosine to the 4th, remember cosine to the 4th I can rewrite as a cosine squared squared. So I can write this as the integral of sine to the fourth x times a cosine squared x squared, cosine x dx. Now I can do a Pythagorean identity substitution here because I know that 1 minus sine squared is cosine squared. So I have sine to the fourth x times 1 minus sine squared times your cosine of x dx. So now is where I'm going to do my u sub. So if u is equal to sine of x, and again that's all squared, du is going to be my cosine of x dx, which is right here. So now I can rewrite my integral in terms of u. So I have the integral of u to the fourth times 1 minus u squared squared du. You are going to have to FOIL out the 1 minus u squared squared. So leave that u to the fourth in the front. So I have 1 minus 2u squared plus u to the fourth du. Distribute that u to the fourth. So I'll have u to the fourth minus 2u to the sixth plus u to the eighth du. Now I can go ahead and I can integrate. So I'll have a u to the fifth over 5 minus 2u to the 7th over 7 plus u to the 9th over 9 plus c. Now I can bring it back in my sine. So I'll have sine to the 5th x over 5 minus 2 sine to the 7th x over 7 plus sine to the 9th x over 9 plus c. So here's an example where sine is odd. Same thing. We're still going to make this out. So it's pull your factor of sine out so we have a linear sine factor in the integral. So I'll have a sine squared x times a cosine to the fourth x times a sine x dx. Again, this is if you're looking ahead on u sub, that's what you want your du to be. So since I want that to be my du, what I want to do somehow, I know the derivative of cosine is a negative sign. So I want to rewrite this whole entire integral in terms of cosines so that this is going to be my du. So here's this sine squared that I can do a Pythagorean identity substitution on. So I have 1 minus cosine squared of x times cosine to the fourth of x times sine of x dx. Now you're ready to do your u sub. So u is equal to cosine of x. Du is your negative sine of x. So I'm going to pull the negative sign out and rewrite my integral in terms of u. So I have 1 minus u squared times u to the fourth du. So I need to distribute. Don't drop that negative sign in front of your integral. So I have u to the fourth minus u to the sixth du. So when I integrate, I end up with negative u to the fifth over 5 minus u to the 7th over 7 plus c. So now I can bring back and substitute in that cosine. But it should be a plus because I minus a negative. So now I need to bring my cosine back in and substitute in for u. So I have negative cosine to the 5th x over 5 plus cosine to the 7th x over 7 plus c.